Alright, welcome to section 4.1. Woohoo! Chapter 4. Chapter 4 is all about systems and matrices. So we're going to start with systems today. Big topic item, what the heck is a system? Okay, so system of equations. Let's do some real world context here. Below is a graph of two types of cameras being sold. One is a digital camera, the other one's a film camera. This is from a few years back because nobody uses film anymore. The graph shows sales of both spans over 6 years, 2000 2005. So we can see that maybe you can't see in yours because it's not color, but blue is film and orange is digital. What conclusions can we draw? Digital is going up and film's going out, right? We can see that film is going down and digital is going up. Notice that the sales of film camera decreased. When were they the same? That's the key question here. When were they the same? Well, for reading the graph, the same would be right about here. Intuitively, we can say they were the same when they both sold $10 billion. When it was $10 billion. Or we could say they were the same in 2003 to 2004. Right? We could say it's that. How would we write the answer to this? We can see where they are the same. It's their intersection point. But what is that point? That point would be 3.5, comma 10, right? That's probably the most accurate. We can say both. They were in 2003 2004 when they both reached $10 billion, pardon me. Awesome. And this is what we call a system. System sounds super complicated, but the word system just means working together, right? Think about your nervous system or your circulatory system or a system of employee management or something like that, right? We have a system, things are working together, they're working to achieve a goal, right? So here, a system of working together just means a couple equations where they are working together, okay? In our systems, we will have two equations like this one. We have a graph. Remember, a graph, from we talked a lot about it, is just a series of dots, right? It's a series that's connected to an equation. In this case, it's connected to two equations. So we'll be dealing with these two equations scenarios more often than not. These ones we can see have kind of weird equations. If you look on the next page, those are the equations there. And they're kind of strange. We're not going to deal with those, but we can see that we can find their intersection by looking at it on the graph. We can graph both of them and find their intersection point. Now, graphing a system is time-consuming, and as we can see, it doesn't lead us to the most accurate intersection point. In this case, pretty easy to see that they both arrive at 10, but we kind of have to eyeball that 3.5. I mean, some may even argue that's more 3.75, 3.76. We can't know for sure, right? So we have other methods, and we will talk about a lot of them in this chapter about how to find that actual intersection point. There are 6 total, including graphing. Graphing is the first one, and it is an option, but it is not the best option. Okay, so we can try to avoid graphing if we can. The first thing we're going to talk about, though, is actually testing what does it mean to be an intersection point. So an intersection point is the solution. It's the solution. Now, we've already have a definition of solution. A solution, if you recall, means an answer. So it works in the equation. We're not going to write that down. I'll just say it. Works in the equation. It's a solution that if I were to plug it into an equation, it would actually match the other side, right? We talked a lot about, what was the one? Way back when we had one that was like 2x plus 3y equals 6. We plugged in 0, 0, and 0 does not equal 6. So it was not a solution, right? For systems, we just have to make sure that any coordinate pair we try to make a solution has to work for both. If it doesn't work for both of them, it's not a part of the system. For example, in this one, if I said the point 2.3 comma 2.1 comma 15 is a solution to this system, I'd be wrong. Even though 2.315 does fit one of them, right? It doesn't fit the other. And so we can't say that it works for both of them because it's not on the line for both of them, right? We're not zooming in on that point. Please recall that it is not an actual line on the page, it is a connection of all the points. So it doesn't have this point common to both of them. But let's check it out algebraically as opposed to visually. How would we test whether 4, 2 was a solution to both these equations? That's easy, just plug them in, right? Let's see if they work in both. Let's see, so 4 plus 2 does indeed equal 6, check, good. And x equals 4 minus 2. And again, I'm not going to rearrange these, I'm not going to like turn them around. I need to make sure the x's go with the x, the y goes with the y, right? So the 4 goes into the x's, the y's go to the 2's. 16 minus 2, yep, that does in fact equal 14. So yes, this would be the solution to the equation. So yes, solution. Now, we're going to talk about this a little bit more, but in 99% of all cases, there's only one solution. Okay, there's only one common point when it comes to a linear system. That's because there's only one intersection. You try to cross two straight lines, you're only going to get one dot, right? Now, if I try to cross other kinds of lines, or other kinds of curves, we call them curves, I could have like a quadratic crossing a couple times, and we'll talk about that. I could have a cubic crossing like 3 times, right? But we're talking straight line to straight line. The most that can happen is it can hit once, right? It can hit once. It's not going to randomly turn around again. So there's only really one solution. Cool. And that's 99% of the time. We'll talk about a couple other cases that aren't necessarily true. All right, let's check this one out. Recommend you try that on your own. Does that one work? Is this one, -1/7, a solution to this system? Okay, hope you had time to try that. If not, please pause the video. I'm going to go ahead and plug it in for x. Okay, let's see. -3 plus 14 does in fact equal 11. Great. -1 is 5 times 7, 6. That is not true. So we would say that no, it is not a solution. It would be so close. If that was a positive one, well, it would have worked in this one, but it wouldn't have worked in the other one, right? So kind of a moot point either way. All right, cool. So now, what if you didn't know the point? What if you didn't know what solution you were checking, right? Step number 1, you could try graphing them. Let's try 1. It's not the best method. I've already mentioned this. It's really kind of time consuming. But we know how to graph. That's all we know how to do right now that we've talked about in previous methods, or previous chapter. We talked about the previous chapter. We know how to graph linears. So at the end of the day, a time-consuming method is still a method that's going to get you points. So make sure you know how to at least do one of these methods. All right, here's my system. Let's solve it by graphing. Let's see where this point would be. Well, they're both in standard form, so we're going to have to rearrange them. Y equals -x plus 5, and -y equals -2x plus 4, or y equals 2x minus 4. Okay, now those I can graph, right? Now, and you can graph other ways. You can do slope-intercept, or I'm sorry, x and y intercepts. You could do point-slope form, like you could just make a table. It's all up to you. But I'm going to graph these using slope-intercept form. For me, it is the easiest. Now, since we're actually trying to find an intersection point and have it be accurate, I'm going to do more than just the 2 dots. Mostly, and really, because my stylus is super sucky. Let's just say that. Okay, so there's the first one. And the second one, I went up 5 and then down 1 over 1. So this one is down 4. You hear my neighbor's dog in the background. And then up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And here we go. And I can already see our intersection solution. There it is. That would be at out 3 and up 2. The intersection would be our solution. That is the point that if I were to plug it in for both of these, they would work. 3 plus 2 does indeed equal 5, and 3 times 2 would be 6, minus 2 would be 4. So yes, this point actually works for both of them. Cool. But that's kind of time consuming, right? That was convenient because I had a graph already on the page. If I'm on a test and I don't have the graph, I don't even know. So what else could we do? Oh no, sorry, let's talk about more solutions before that. So I mentioned that this is what happens in 99% of cases. You can see that right here, right? We get a point. Something else that can happen, parallel lines. We talked about those last chapter. Parallel lines will never intersect because they start at different points, but they have the exact same slope. No matter what, they're not going to run into each other. So this is what we call no solution. There are other names. One of them is called a inconsistent system and a dependent system. You don't have to worry about that. If you see something in the homework like that, just shoot me an email real fast and I'll replace it. But this is a no solution situation. The third case is where you actually get two of the same line. You're like, Miss K, wouldn't it be obvious that you had two of the same line? You would think, but not really. So in a system, what can happen is you have something like this for your first equation, but then your second equation has just been multiplied to everything. So something like this. And you may not realize that those are actually the same equation, but all I've done is taken the first equation and multiplied it by 2. So if I divide the second equation by 2, I have the same thing twice. And when you have the same thing twice, it's just lying on top of each other. Now it's kind of hard to see in your note packet, but that's kind of why I put these as red and blue and this one is purple, to show that it's two equations, but they're giving you the exact same points because if you try hard enough, they're actually the same equation, right? So they're kind of lying on top of each other. And that means every point's in common, so it's actually an infinite number of solutions. So you can have two problems here. You can have ones that are parallel. Parallel lines would be something like this, where they're almost the same, but no amount of math is going to make those the same. And then there's ones where they're exactly the same, and that's infinite solutions. Okay. The second two are uncommon. If you get them, just know that they exist. Okay, and with all of our different cases of how to solve these, I'm going to show you how to recognize them. This is how you would recognize it graphically, is you would see the parallel line, or you would see the double line. All right, cool. So that was method number 1. Congrats, you're already 1/6 of the way done. Yes, there are 6 different ways to solve these, but there's a reason we're going over all 6 is because it's super important. So here we have our second method. This is by substitution. Substitution is probably one of the most convenient methods because you can do it with nonlinears. You can do it with stuff outside of this. Anyway, so substitution gets the method is the name. We are going to substitute. Okay, so we're given our system here. Right, we have a system. It is given us to a slightly different format as the first one. We can see that that second equation has already been solved. Now that doesn't necessarily mean we have to only use substitution here. It also doesn't necessarily mean that it has to be set up this way to use substitution. You can use substitution anywhere. We could have done it on the first one. But for this one, it's very convenient because something is already solved for. Okay, so let me show you how this works with something you're familiar with first. If I had that first equation, but I said this instead of y plus 2, what would you do? Well, you would take 2 and you'd plug it in for x, right? You would just plug it in and you'd get what y was. Same exact idea. Same exact idea, except instead of plugging in 2, I'm going to plug in y plus 2. I'm going to plug in this whole thing. And that really does not break any rules, because I know that x equals y plus 2, so why not just write y plus 2? This is the substitution step. I have taken this and I have plugged it in there, because that's what x equals. Just like if it was x equals 2, and I would plug it in like that. Same exact thing. But technically technically I can solve this the same way now. Notice in this one I got rid of the x, I just have y, I can solve for y. Here I may have 2 y's, but it's still only y's, and I can solve an equation with one variable. I can solve those, I can figure out what y is. So I just have to do a little bit more maneuvering though. Then combine like terms, you get y plus 4 equals 6, so y equals 2. And please recall, I don't spend a lot of time in the video doing the equation parts in class, the solving parts. If you need help with that, come see me. Totally fine. Okay, so y equals 2. Unfortunately, that's not where we're going to stop. Not really unfortunately, but that can't be where we're going to stop because there are 2 variables here, right? We want to make sure we have the whole solution, not just the variable. So y equals 2, that's great, but what does x equal? Well, we can choose either one of the equations. In this case, maybe the second, right? X equals y plus 2, and we can plug in our new information, the fact that y equals 2. And so x equals 4. 4 comma 2 is our solution. That is the place where these are going to intersect. So that's how we do substitution. We take one variable out by substituting in an expression, solve for that variable, go back and solve for the other one. And no, you don't have to substitute y in. You can substitute x if it's more convenient, right? You can solve for x. Some cases it's equally convenient and it's totally up to you. Okay, so let's try it out again now with a couple more. And then in 4.2, we'll talk about our next one. Highly recommend you try these on your own before we do them together. I will give you a second to try and pause the video. Okay, so we're back now. Let's try this with substitution. This one is not set up for substitution. Kind of like I was mentioning, it doesn't have to be set up for it, but we can make it set up for that. Let's make this, let's see. There are 4 different ways to solve this for substitution. Okay, these have a lot of maneuverability. There's really, unless you like break a rule of math, like 2 plus 5 is 8, right, because 2 plus 5 is 7, you can't do this wrong. You kind of can't do this wrong unless, you break a rule of math. But I'm going to pick one that I think would be most convenient. I think this one. I think I'm going to solve for that guy. If I solve for this one, I make a y equals, then I could substitute in y. Do I have to choose that one? No. I definitely could have solved for this one. I could solve for this one. I could solve for this one. Those are the 4 different ways you could do this. But since that y only has a negative in front, kind of in a sense already by itself, I'm going to solve for that one. So we're going to go over here. Is that negative one? Yeah. Solving for y, you get negative y equals negative 4x minus 1, y equals 4x plus 1. Great, I solved for it. Now I'm going to take this information that y equals 4x plus 1, I'm going to take the other equation, 13, yeah, and I'm going to take out y, 3x plus 2, and plug in what we just solved for. And that's the substitution step. That's the step where I substitute out y and I put in what it equals. Okay. This has only x's, so I can solve that. 8x plus 2 with some distribution, 11x plus 2, and so x equals, actually I'm going to go over here now, 11x equals 11. And so x equals 1. Now I got to make sure that I actually plug that back in and figure out what the y is, but hopefully that solving wasn't too bad. Again, if you need help with that, just come see me. The best part about substitution, though, is I don't necessarily have to go back to these versions of the equations. While these are valid and would totally work, I've already rearranged one of them so that it would be super convenient to find y, and I can use that one. Now if I plug in what I know, I can figure out that y equals 5 pretty quickly. And so my solution would be 1, 5. Oops. There we go. Awesome. All right. We're going to do one more. I may want to do one more after this. Go ahead and try this on your own. In this one, it doesn't matter which one you choose. Choose whichever one you want. I'm going to go with the 2. I'm going to go the 2x route. Okay, so I have 2x plus 3y equals negative 6. Move that 3 over. Oops. 3y minus 6, negative 3y minus 6. X equals negative 3 halves y minus 3. Okay, now I'll go plug that into the other one. 4x minus 3y equals 22. Yep. 4 times negative 3 halves y minus 3 minus 3y equals 22. Okay. Yeah, sometimes substitution ends up with fractions. And no matter which route you went in this one, you probably would have ended up with at least one fraction. I just like 2. Dividing by 2 is pretty easy for me, so I just went with that one. 4 times negative 3 is 12, divided by 2 is negative 6. Negative 12. If you didn't follow that, that's just fraction multiplication, so come see me. I'd be happy to help you out. It's okay to be stuck now. It's not okay to be stuck on the test. Combine like terms. Negative 9y minus 12 equals 22. Add that negative 9y. Oh, that's a 4. Oh my goodness. Okay. Stylus is starting to bug me. $34? Okay, that's a weird number, so let me just double check my math real fast, just in case. That would be negative 12. Over here. Minus 3. 3 halves. Minus 3. Negative 6. Yep. Okay. And then that was good. Minus 3y. Yep. Minus 3y. Minus 12. Yeah, it's all good. Okay. It's just an ugly number. So we get y is equal to negative 34 over 9. Plug that back in. I think I'm going to plug it into this one because yuck. And x equals negative 3 halves. 34 over 9 minus 3 is going to be 34 times 3 divided by 18 minus 3. 2.6-ish. 2.6 as a decimal would be 2 2/3 or 11/3. Six, 7, 8. Nope, just kidding. 8/3. 8/3. Okay, so our final answer: 8/3, comma negative 34 over 9. Not pretty, but a solution. And this is where substitution can give us a much more accurate answer. We don't want to double check our math because even I was like, wait, that's really weird. But it ended up being ugly. It lets us have a more accurate answer where the intersection points are, as opposed to like, kind of 2 and kind of negative 5 or whatever that is, right? Negative 4. It's more accurate. Okay, so don't panic when you see fractions. One other thing before we go on, I want to show you just one substitution of a parallel. Okay, I want you to see what happens. So if I had 3x, let's go back to that parallel we had. Let's see. 2x plus y equals 6 and 2x plus y equals 5. So what happens, we solve for y, right? Pick which one you want. Sorry, you can hear my son crying in the background. Y equals negative 2x plus 5. And we plug that into the first one. 2x plus negative 2x plus 5 equals 6. What happened? These are going to cancel, and 5 does not equal 6. Okay, we get a weird sentence. So you get some cancellation here. The same thing happens in the inconsistent system, the one that's like double, right? The infinite solutions. But what you get is like 6 equals 6. So just watch out for that. Don't worry about it too much. If you get something that's not working out, triple check your math. Okay, a fraction does not mean it's not working out. What it means, if you get something like this, though, where variables are canceling, like everything is canceling too much, you may have a set of parallel lines or the same line. Okay. All right, that is 4.1. Shoot me an email if you have any questions.